All right, we've got our model all set up. We're ready to run this thing. So I'm going to go to Analyze, and I'm going to go to Set Options. And one little, it's not an absolute requirement, but I would suggest you just do this clicking on the plane frame option is probably going to help sort of stabilize things and ensure our model actually runs. So I'm going to go then back up here. I'm going to do run, and then up will pop this. And I have to tell SAP where I want to put this thing. So maybe I'll go here and see if I can open a new folder. I'm going to call this hybrid maybe. And give the file a name, beam, and beam, Perth. Yeah, well, it was inspired by a trip to Perth, so I'll call it Perth. Okay, click save, and then off we go. By the way, I'm just going to do a quick run back through here. One of the things you'll notice now that we are going through and talking about the matrix method, you'll notice there's a bunch of text here that we haven't gone through, I haven't really talked about before, but notice it talks here element formation. All right, element formation. So what's it doing there? It is setting up the element stiffness matrices for each of our different elements. Equation solution here, it's basically now has set up the loading vector, the displacement vector, and then the stiffness matrix, and then it's going through and solving. You can see the number of equations it has to solve. It's got some warnings there, but everything seemed to be fine, and then it continued on and said analysis complete. So that's good. So I'm going to click OK. And what I've got is the deflected shape. You'll notice that the truss members have stayed straight, and they should. The way we define it with just the pin-ended members, these should just be subjected to axial forces, either tension or compression. But you'll notice your beam has a nice curved shape there, and that's good because we have those loadings. Well, it's consistent with what we're trying to model here. So because we have loadings applied along the length of that member, that's not going to stay straight. It's actually going to undergo bending. And in fact, we can click on any of these joints, and if we right-click it, up will pop this. So it says translation. Remember, these are going to be in units of meters. And we'll notice in the one direction, that's going to be on our X direction. The 2 is in the Y direction. That would be into the screen. But 3 is in the global Z direction. So you can see here we got a negative 0.004 meters. So that would be about 4.3 millimeters downward deflection. And if we right-click on this joint, see we get here about 0.407 millimeters of deflection at that bottom of the truss. Okay, I think for the assignment we were asked for things like the axial forces in the in our system. So we'll go up here, we'll go to this member force icon up here and click on that, and then we have our different options here. So previously we just looked at axial force. Let's go OK. So we can see what our usual drawing, and we can right click on these and we can see those diagonal members. We get about 35.9 kilonewtons in tension, and then that middle member about 22.72 kilonewtons, the negative sign indicating its compression. Notice the beam also has an axial force. How much is that? Let's right click on that. 34 kilonewtons, so in compression. So pretty big compressive on that beam. So that's different from what we're used to thinking of beams as just having shear and bending moments. Because we've added in these axial members, they're creating horizontal components that are leading to this compression force in the beam. All right, now anything else going on? Let's go back up here. So when we had trusses, we didn't worry about shear and moments, but now we are going to worry about it. Okay, so this 2-2 and 3-3 for the shears, 2-2 and 3-3 for the moments. So these are referring to local axes, and I'll talk about this a little bit more in a later video or in lecture. But basically, for this problem, what we want is the moment 3-3. That will give us the moment diagram that we want. Actually, let me click on the M22 and let me go here and go OK. If I click on it, you'll notice nothing shows up. So M22 would actually be bending into the screen, and obviously we're not going to get bending in that direction. So M33 is the one that I want, and so what am I seeing here? Notice that those pin jointed members, there's nothing showing up. If I right click on those, okay, nothing. And that's good. That's exactly what it should be for a truss member. But we are seeing bending happening in the beam. Now, you may be wondering a little bit about the shape of this. Let me go over here to options. And when I go to options, what we see here, clicked here, is moment diagrams on tension side. That is the default bending moment convention for SAP. We have been using in our course the convention of bending moments plotted on the compression side. If I unclick that, they flip over, and then that's consistent with what we would usually expect for our bending moment diagrams. Interesting shape, right? So we're used to a beam with a pin and roller support having like that big parabolic with a maximum moment in the middle. Adding in these rods has completely changed the shape. Let's take a look. Let's right click each one of these beam sections and we get a diagram that looks like this. Notice as I move my cursor along, it's giving me different distances along the length and the value changes. So as I scan along, I can see where, what is my maximum value here, somewhere around what, 17.36 kilonewtons, occurring at a distance of 1.88 meters from the start of that element. So that then gives me the magnitude and the location of that maximum moment. And just to check on the other side, I'm getting the same numbers over there as well. So that's good. That's what I would expect given the symmetry. Now, another thing we may want to look at would be the shear forces. So for the shears, the one we want to pick for this problem is shear 2-2. Okay. In fact, if I'll just show, if I pick shear 3-3, I get nothing. Okay, so shear 2-2, I click on that and then OK, and I get some shear diagrams that look like this. I will point out to you that the shape of these are probably going to look familiar, but you're probably expecting those shear diagrams to be the mirror image. So in other words, the shear to be plotted on the other side of what is actually being shown here. So what I can tell you is that the convention in SAP for shear, well, I'll talk about it in a later video, but basically what you can see is that this is the opposite sign convention to what we're used to in usually in our course. If I right click on that member, again, I can see over here on the left, I've got a maximum value of 18.64 kilonewtons at the end. We would probably be plotting that as a positive shear, but that's fine. We can see where our shear value becomes 0. That's, of course, where we would get our maximum moment, somewhere along, well, 1.86 or so. And then over at the other end, we get 11.36 kilonewtons for the shear value. So those are the different values you're probably going to need for this particular assignment. What else? If we want to make some changes, so in this assignment, let me pull it up, you are asked to kind of investigate what happens if we change the size of those rods. So if we change the diameter, for example, to 50 millimeters or reduce it down to 10 millimeters, how would that change our internal moments? So for that, what I would suggest you do is come over here. You see there's a little lock. You have to unlock that. So click on that, and that will unlock the model. Notice it's actually going to delete all of your results, but that's okay. We're going to do a new analysis here. And then what I'm going to do is go to Define, Frame Sections, click on the rods, Modify Show Section, and I can simply, in there, change the diameter. I'll make it 50 millimeters. Click OK. OK. Everything else should stay the same. I'll run the model. And then I'm going to go OK. And then, for example, I can then go and check out my moments. Click OK. Ooh, very different. Something's changed, right? Something's changed. So as we've stiffened up those rods, that has massively changed that bending moment diagram. Let me right click on that, and we can see we're getting some differences in those maximum moments for sure as compared to the other setup. So hopefully that's enough to get you rolling on this assignment. And in fact, that should give you some pretty good tips on how to model, in fact, any beam and different types of loadings on different beams, which you may have in some future assignments. All right, that's it for now.